Welcome to G Fun Facts Online. Today we are diving deep into one of the most sophisticated pieces of optical engineering ever conceived, a machine designed to solve a problem that has plagued astronomy for centuries. We are talking about the Roman Coronagraph Instrument, or CGI, aboard NASA's upcoming Nancy Grace Roman Space Telescope. The search for life beyond Earth is arguably the most profound scientific endeavor of our time. For the last 3 decades, we have been in a golden age of exoplanet discovery, confirming over 5,000 planets orbiting other stars. But there is a catch. We rarely actually see them. We detect them indirectly, by the wobble they cause in their host star or the tiny dip in brightness as they pass in front of it. To truly understand these worlds, to analyze their atmospheres for signs of water, oxygen, and potential life, we need to capture their light directly. We need to take their picture. And that is incredibly difficult. To understand why, and to understand the genius of the Roman coronagraph, we have to start with the tyranny of starlight. Stars are billions of times brighter than the planets that orbit them. In visible light, our sun is 10 billion times brighter than the Earth. Trying to image an Earth-like planet next to a sun-like star is often compared to trying to spot a firefly hovering next to a stadium floodlight, but the observer is located several thousand miles away. The problem isn't just raw brightness, it is the nature of light itself. Light acts as a wave. When it passes through the circular opening of a telescope, it diffracts. It spreads out, creating a pattern of bright rings and scattered light called the point spread function. This diffraction pattern acts like a luminous fog, completely washing out the faint signal of any nearby planet. For a long time, this seemed like an insurmountable barrier. The traditional solution is a device called a coronagraph. The story of this instrument actually goes back to the 1930s in the French Pyrenees. An astronomer named Bernard Lyot was frustrated because he could only study the sun's faint outer atmosphere, the corona, during the fleeting moments of a total solar eclipse. He realized that if he could create an artificial eclipse inside his telescope, he could study the corona whenever he wanted. He invented the coronagraph, a device that places an opaque metal disc at the focal point of the telescope to block the sun's image. It revolutionized solar physics. But doing this for distant stars is much harder. When the Hubble Space Telescope launched, it brought coronagraphy to the stellar stage. Hubble's instruments allowed astronomers to block the light of distant stars to look for debris disks, the dusty rings where planets are born. But Hubble's coronagraphs were passive. They relied on the static precision of the optics. The problem is that space is a dynamic environment. As a spacecraft moves, the thermal load from the sun changes, causing the telescope structure to expand or contract by tiny amounts. Vibrations from reaction wheels can jitter the optics. In a passive coronagraph, a shift of just a few nanometers, the width of a few DNA strands, can cause enough starlight to leak around the mask to hide a planet. Hubble could suppress starlight by a factor of about 100,000. To see a Jupiter-like planet, we need a suppression of 100 million. To see an Earth, we need 10 billion. That is the gap the Roman coronagraph is designed to bridge. It is not just a camera, it is a technology demonstrator, a Class C mission designed to prove that we can actively manipulate starlight in space. The Roman coronagraph is roughly the size of a baby grand piano, nestled within the telescope, but inside, it operates with nanometer precision. It moves from the passive suppression of the past to active wavefront control. This is the heart of the machine. The instrument contains 2 high-precision deformable mirrors, or DMs. These are not static glass surfaces. They are flexible membranes polished to angstrom-level smoothness, resting on a bed of thousands of piezoelectric actuators. These actuators can push or pull the mirror surface, creating microscopic hills and valleys. One mirror, the pupil mirror, corrects for errors in the telescope's primary mirror. The second, The field mirror works in concert with the first to create a dark hole, a specific region where starlight is destructively interfered with to near zero intensity. This forms a closed feedback loop. The instrument constantly measures the incoming starlight, calculates the errors caused by thermal expansion or jitter, and commands the mirrors to flex and compensate in real time. It is similar to the adaptive optics used on ground-based telescopes to fight atmospheric turbulence, but instead of correcting for the fast blurring of the atmosphere, Roman corrects for the slow, insidious breathing of the telescope optics. Once the light is corrected by the mirrors, it has to be blocked. Roman employs two distinct types of masks. The first is the hybrid light coronagraph. Think of this as the sniper rifle. It uses a complex mask that combines a metal blocker with a dielectric layer that shifts the phase of the light. It offers a 360-degree field of view around the star and allows us to see planets very close to their host. The second type is the shaped pupil coronagraph. This is more like a shotgun. Instead of blocking light at the focus, it reshapes the telescope's pupil with a binary pattern of openings. This forces the diffracted light into specific lobes, leaving two bow-tie-shaped dark zones. It is incredibly robust against telescope vibration and is the preferred mode for spectroscopy. But suppressing the light is only half the battle. You still have to catch the photons from the planet. The signal from an exoplanet is incredibly faint, often just a few photons hitting the detector per second. Standard cameras have read noise, electronic static added every time you read the data. If your planet only sends 5 photons and your read noise is 10 photons, you will never see the planet. Roman uses electron multiplying CCDs, or EMCCDs. These detectors operate in a photon-counting mode. When a photon hits the sensor and frees an electron, that electron is passed through a high-voltage register that accelerates it, crashing it into other atoms and freeing more electrons in an avalanche effect. One electron becomes 1,000. This amplifies the signal before it is read out, effectively reducing read noise to 0. Roman can literally count the individual particles of light arriving from a distant world. The process of combining all these technologies is called digging the dark hole. When the instrument turns on, the image of the star is a messy blob of speckles caused by optical imperfections. These speckles look exactly like planets. To distinguish them, the instrument runs an iterative cycle. It uses the deformable mirrors to probe the light, mapping the electric field of the speckles. Then, the computer calculates the exact shape the mirrors must take to create anti-speckles, waves that destructively interfere with the stray light. It applies the correction, and the background gets darker. It repeats this process over and over. Eventually, the starlight in the target region is suppressed by a factor of 100 million. In the center of this artificially created void, the steady light of a planet can shine through. So what will Roman actually look at? Because this is a technology demonstration, it will start with bright, nearby stars, likely those magnitude 2 to 5, where we already suspect planets or debris disks exist. A prime candidate is 47 Ursae Majoris, a yellow dwarf star known to host gas giants. The science potential here is specific and groundbreaking. Current ground-based telescopes can mostly see young Jupiters, planets that are freshly formed and still glowing hot with infrared heat. They cannot see cold, mature Jupiters like our own, which only shine by reflected starlight. Roman will be the first instrument capable of imaging these cold giants in visible light, completing our family album of exoplanets. It will also study zodiacal dust, the debris from comets and asteroids that fills other solar systems. This dust is the background noise for future Earth hunters, so we need to know how much of it is out there. Perhaps the most exciting capability is spectroscopy. Roman includes a prism that can disperse the faint light of a planet into a spectrum. By analyzing this light, astronomers can look for absorption lines, the fingerprints of chemical elements. In the reflection spectrum of a gas giant, they might see methane clouds or ammonia ice. While Roman won't be imaging Earth twins, demonstrating the ability to take a spectrum of a dot 100 million times fainter than its star, is the technological hurdle we must clear to one day detect oxygen or chlorophyll on a habitable world. This leads us to the ultimate goal. Roman is the bridge to the future. The National Academy of Sciences has recommended a future flagship mission, the Habitable Worlds Observatory, specifically designed to find life on Earth-like planets. To do that, we need a coronagraph 100 to 1,000 times better than Roman's. Roman is the prototype. It validates the physics of active wavefront control in space. It provides the ground truth for our models. If the deformable mirrors and photon-counting detectors work on Roman, NASA can build the Habitable Worlds Observatory with confidence. When the Nancy Grace Roman Space Telescope launches, its most exciting images might look like almost nothing to the untrained eye, just a black square with a few pixels in the center. But to an astronomer, that blackness is beautiful. It represents the conquest of diffraction. It represents a dark hole where the blinding light of a star has been tamed, allowing the faint reflected photons of a mature planetary system to reach us for the first time. It is a declaration that we are no longer content to infer the existence of other worlds from shadows. We are ready to look them in the eye,